Radiative forcing. The Earth is often, with reasonable accuracy, modelled as a black body, meaning the incoming energy equals the outgoing energy in theory. With the added modelling of the atmosphere as another black body, this diagram demonstrates the balance of incoming and outgoing types of energy per square metre. Written as an equation here, Ts is the Earth's surface temperature, Ta is the atmosphere's temperature, theta is the Stefan-Boltzmann constant, and S0 is the solar irradiance. This energy balance is known as the Earth-atmosphere system. The measure of how much a factor has influence on altering this Earth-atmosphere balance is known as radiative forcing. Dependent on when and where the flux change is measured, determines the specific type of radiative forcing. Measuring prior to any natural adjustments is known as instantaneous radiative forcing. Measuring at the tropopause, after allowing the stratosphere temperature to adjust, is just radiative forcing. Measuring at the top of the atmosphere, post-fast atmospheric adjustments, is known as effective radiative forcing. This is usually the most representative of the effect on the climate system. Allowing everything to adjust and measuring at the point of net zero flux is the equilibrium response. Using the umbrella term of radiative forcing for the general description of the measured influence, we can either observe positive or negative radiative forcing. Positive radiative forcing. Positive radiative forcing is where there is more incoming than outgoing energy towards Earth, causing an increase in the Earth's surface temperature. Many examples of this are the factors responsible for the increased rate of climate change. Examples include melting snow and ice. As the white snow and ice melt, revealing the darker land beneath, the albedo of the surface decreases, as indicated through the diagram in a simplistic form that highlights the difference between the reflective power of different colours. As this process itself is triggered by increased surface temperatures, this produces a climate feedback loop, meaning that the issue is accentuated over time. Ice melting also releases trapped gases, such as methane, leading on to our next positive forcing example, greenhouse gas release. Greenhouse gases in the atmosphere, such as CO2, water vapour and methane, absorb solar radiation, distribute it through the atmosphere, and then re-emit it in all directions, including therefore back to Earth, in a process known as the greenhouse effect. A certain degree of this is necessary in order to keep the Earth at a livable temperature, but excess produces excessive heating. Alongside their release from melting ice, major releases of greenhouse gases are from manufacturing processes and producing energy from burning fossil fuels, as well as transport. Out of the different greenhouse gas releasing factors in the UK, domestic transport was the highest contributor, producing 26% of emissions according to the government in 2021. Negative radiative forcing. Negative radiative forcing is where the Earth is emitting more energy than it receives. This causes a cooling effect for the Earth's surface. An example of this, volcanic eruptions. The sulfur dioxide released by a volcanic eruption reacts with the water vapour in the stratosphere, creating sulfuric acid droplets. These are highly reflective sulfate aerosols that reflect solar radiation back into space. This increases the Earth's albedo, leading to a lesser absorption of energy, causing this cooling effect. These sulfate aerosols are also being discussed to be released anthropogenically to mimic the cooling from volcanic eruptions. However, the natural expelling of sulfur from the stratosphere can cause negative environmental impacts such as acid rain and impacts on human health. As negative radiative forcing options without risks are limited, it appears that combating climate change is about limiting positive radiative forcing mechanisms. Thank you for listening.